Welcome back, everybody. Today is Thursday, October 10th. The announcements, if you wanted to see them, are right here. We've already looked at them. But we also know that Filipinos celebrate Christmas longer than I think, which I did not know that. The Philippines takes Christmas celebrations to the next level, beginning in September and lasting until January. The Feast of the Three Kings. The festive atmosphere includes decorations and numerous parties. Like, for real, if you were to go to Manila right now, there's already a Christmas tree up.
Yeah.
That's insane.
There's like lights, like I wasn't there in the summer and they were already have so much stuff in it.
That is crazy. Okay, cool. I enjoy Christmas. I'm really looking forward to it this year because my kid's old enough to understand, and I'm gonna be Santa and go knock on reindeer. So it's gonna be fun. Anyway, here we go. We get to start 4.2. And in this section, we're gonna be talking about two things. Weight is one of them. Weight and drag. And specifically drag force. All right. Now, the cool thing about the drag force idea, which maybe you guys know of it, when I say drag force, does anything come to mind? Friction. That's fair because you're thinking about dragging something across the floor. My mind goes right to parachutes or drag racers specifically because, like, Formula One cars and stuff, it's super cool, the physics of them. They go crazy fast and they're not very heavy. So they could actually, if you were in a tunnel, a circular tunnel, a Formula One car at full speed could drive upside down, like on the ceiling, because there's so much force pushed down by the spoiler on the back of the car because it needs to be able to keep itself on the ground. They're crazy. They're awesome. All right. The good news is that this idea of drag force, it makes me think of falling through the air. Like, I don't know, how do we increase the drag force to make something slow down so it doesn't crack when we drop it in the hallway next week? Just throwing it out there. All right. So, we're going to start today by the discussion of weight. And this is going to be a definition. Weight. Did I ever tell you guys a story about why I say it in such an odd intonation? Where I went to college in Laramie, Wyoming, there's stoplights, obviously, because it's a university. But on all the stoplights around the university, they're made for access to, like, blind folks and stuff. Which, if you've never thought about it, using a crosswalk as a blind person must be like the most stressful thing ever, like realistically. But the stops lights in Laramie near the university, like you'd push the button and it'd go, time starting, wait, and it would be really aggressively telling you to, like, just don't go yet, don't go. And I can't say it without thinking of that. I take it you've seen them.
Yeah, there's some places.
Wait.
If you press it like 5 times in a row, like wait, and like a pre-recorded message will come on, and the guy will be like,
Quit pushing my buttons.
wait.
All right. So, if I asked you guys what is weight, just gut feeling, how do you explain it? That is a natural way to go about it. I'll tell you, it's not, which is a weird idea. You've been lied to your whole lives. Big weight scale manufacturers have. I don't really have a conspiracy here. It's not right. It is not correct. When we talk about weight, the idea of how much you weigh, like, that's what we use, right? And you're going to associate it with mass because in our world, in our culture, our civilization, however you want to word it, we've said the two are essentially the same. Now, we don't have to, and we don't in physics, and I assume eventually this will change. If I asked you guys your weight, and I'm not going to, but would you know it? Like, I know roughly what I weigh. I haven't stepped on a scale for a little while, but I'm about 200 pounds. That's what I assume I'm at right now. Pounds, first of all, is not the right unit because that's not metric because we're in a physics class. But I'll tell you, kilograms is also not quite the right unit. When we talk about weight, it is literally just the gravitational force. The gravitational force experienced by an object or by a mass. Now, this has pretty huge implications. As we look at this, this isn't going to be a surprising fact. If I were to step on a scale here on Earth and I weigh 200 pounds, if I step on a scale on the moon, do I still weigh 200 pounds? No. Why? Yeah, different strength of gravitational force. However, if my mass is 200 pounds, because I don't know my weight in kilos, probably about 75, is my mass still 75 kilos on the moon? Definitely. The same amount of stuff is still inside of me. It just has a different strength of gravity. Now, as we look at this, we get to use Newton's law here a little bit more. So remind me, Newton's second law is force is equal to what? Mass times acceleration. And we're going to see something here that I want to make sure we hit clearly enough that we can all walk away understanding it. So, if we say weight is just the force of gravity, I'm just going to say Fg. The force of gravity is literally weight. We're not going to write W. We're not going to write the word weight. We're just going to say the force of gravity acting on something, because that's what it's defined as. Now, we know that this is specifically m, the mass, times the acceleration. And I'm going to go a little bit more specifically. Acceleration varies depending on where you are in the universe, right? Now, we're looking at the acceleration due to what? The force of gravity is just the mass times the acceleration that's caused by gravity. Does that seem reasonable? Okay, we're going to use a little subscript here again. Now, alternatively, this can get misleading. The more subscripts and stuff, like, it starts to look kind of ugly. So what we can do, and I've seen some of us already doing it, is we can say that Fg, to make it a little bit simpler, or not, I'm not sure, is just mass m. And instead of saying the acceleration due to gravity, we're just going to use this g. It's regular standard g. Now, in this is the same formula, but we're going to clean it up just a little bit to make sense of it. Where this g right here, this big one, g is the gravitational field strength. Okay. Here's the weird little part that maybe it's not really that weird. You guys know what the acceleration due to gravity is, I think. On our planet, what is it? What is the acceleration due to gravity on Earth? I'll take 9.8. It's 9.81 is the standard number if you're going to use 2 decimals. But we know it's 9.8 meters per second squared, right? So these numbers are identical, but contextually we can think about them just a little bit different. I know that the acceleration due to gravity, a sub g, is equal to 9.8 meters per second squared. And it's downward, but I'm not going to indicate it with negative. I'm just going to highlight that, yep, I know it. All right, here's my challenge for you. I'm going to say that g, which is a gravitational field strength, the thing that causes an acceleration here, I'm going to make a claim that this instead is 9.8 newtons per kilogram. And I have a quick little fun fraction unit game for you to play. I want you guys to answer the question really quickly. Are these the same thing? Okay, when I'm asking you to make that determination, 9.8 meters per second squared, that is an SI unit all the way through, right? It's derived, but it's meters, which are SI, and seconds, which are SI. Is 9.8 newtons per kilogram straight up just SI units right now? So I see yes, no, and I think you could make the argument either way realistically. What's a newton? And rather than just answering it, try to do newtons over kilograms using the SI units of kilogram, like whatever the newton actually is, and see if they're the same. I don't know if that makes sense or not. Okay, thank you for your honesty. In your work, what I want to see is newtons per kilogram. I want you to verify and check, is this equal to meters per second squared? Now, my goal and my suggestion, because I don't want to work with both sides of something in case they're not, right? Because this is essentially an identity. I want you to manipulate only this side and see if you can get it to become this. Change newtons into whatever you know they are and see if it comes out as meters per second squared. I'll give you a moment. Does it work? Okay. Now, yesterday, just as a reminder, when we put a 1 kilogram mass on our spring scale, how many newtons did it tell us? Do you remember, Nick? Because you're the one that weighed it. 1 kilogram spit out how many newtons on our scale? When you weighed this with that spring scale yesterday? When you did half, what did it spit out? So half a kilogram was 5. And do you agree that that number, 9.8, is pretty close to 10? Like, we'll just use 10 for thinking purposes. If I said that, man, 10 newtons per kilogram is the force of gravity, then if I had half a kilogram, you would expect 5 newtons, right? We saw this experimentally just as you weighed stuff. This does in fact happen. If you're looking for the math of it, I'm just going to clean this up. What's a newton? And I need a better way to ask this question. What's the label or the unit that we'd use and simplify using a newton? So we would get kilogram meters per second squared divided by what? Here's my newton. Still dividing by kilograms. Okay. How do you clean this up mathematically to make it look nice and easy to think about? I think Usher uses this lyric pretty regularly. Maybe not. I had a different joke in my head. I was trying to think, whoa. Oh, yeah, that's it. Doesn't Usher the guy that goes, whoa, oh, da, 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 and this is the whoa. So it does connect. What happens? Help me rewrite this. Kilogram meters per second squared.
Is that a G?
Which one?
The green one.
This is NES. So a newton is a single kilogram meter per second squared. So I've just replaced newtons here, and we're dividing by kilograms, but fractions over fractions sucks. So what am I going to multiply by? Okay. We're going to take one quick step back because I can't tell. I'm dividing by kilograms over 1, right? It's a fraction divided by fraction. And can you say that louder, Fern? That's like multiplying by what? 1 over kilograms. Does anything nice happen here? Shuta. Okay. Are they the same? Yes. Right off the bat, I can see it. They're the same. Depending on the context, newtons per kilogram might be easier to work with rather than kilogram meters per second squared, especially once you start playing the unit game. Because if you have a mass in kilograms times a force in newtons per kilogram, or acceleration or gravitational strength or whatever you want to call it, then kilograms fall out right off the bat. What I mean by that is, let's go ahead and check it out. Okay, so we're just going to do a really quick, easy example. And if you structure your notes like me, does everybody have space right here to do it? Just a quick little example right here in your notes. Okay, I want you to find the weight of a, let's say, 7 kilogram mass on Earth. Now, this problem, we could go through all the knowns and stuff, and maybe, like we should, because I should model that every time. What do you know in this problem? So we know the mass. Got it. What is the mass? 7 kilograms. All right. Here's the harder question that this is where it's going to see if we really connected it or not. What else do I know? On Earth. Now, there's 2 ways that you can present this idea, but I'm going to make sure we use the new one. I could write down that I know the acceleration. Do you guys agree with that? Alternatively, because I'm looking for weight and I know that it's mg instead, I'm going to write down g. And on Earth, the gravitational field strength, g, is 9.8, but it's not meters per second squared. It's what? Newtons per kilogram. Now, you will get the exact same thing if you just call it acceleration, but we're taking some like nice steps to make these units easier to work with. What are we trying to find? Ooh, love it. I was expecting somebody to say weight. We are finding the weight, you're right, but I'm not going to write W. It's the force due to what? Gravity. It is the force, absolutely. Okay, so let's just check it out. There's an equation. It's Newton's second law, it's just worded a little bit differently. The equation that we get is the force of gravity is exactly equal to the mass times the gravitational field strength. And here's the unit game that's going to show up, and this is why we're taking the time to do it. The mass I know is 7, and I'm going to play the unit game underneath. Kilograms times, what's the gravitational field strength? 9.8, and what's its unit? Not just newtons. A little bit more, whoever murmured newtons. I think it was Mickey, but I could be wrong. Newtons per kilogram. Why am I pushing this idea as a nicer version? Shweta. What are we left with? The only unit. Newtons. Is that what we should be left with? So let's see. 7 times 9 is 63, plus 5.6 is 68.6. Newtons. If anybody has a calculator, you can double check my math, but if that's the only mistake, I'm not too worried about it. Now, yes. As we look at it then, here's the big idea. If I ever ask you for the weight of something, the unit that you will be left with is going to be what? Newtons. That is such an important idea, we should jot that down. The weight of an object is in newtons. Every time. Don't give me a weight in kilograms. Don't give me a weight in pounds or grams or whatever. Nope. I need newtons if we're talking about the weight. Now, this section, gosh, this is just fun stuff that's intuitive until you start looking at the math. For me, anyway. If you're on a scale, it reads your weight to you in pounds. Like, it's not really your weight, but it gives you pounds, right? Or kilograms. You could probably find one that does that. So forth and so on. How does a scale work? Anybody ever thought about it? Probably not, based on your expressions. That's reasonable. Okay, so scales, the way that they work is there's springs inside of them. Now, when you step down on a spring, it compresses, right? So if I have a bunch of springs that are all set up and aligned to be some amount of reactive, when I step on a scale, I'm going to push down the springs, yeah? Okay, as I push down those springs, they're calibrated with that dial that turns to say, oh, when the springs, if they compress this much, you read out this number, and it's just 1 to 1. Just depends on how much I push down on it. There's nothing too crazy about it. Now, it gives us our weight in pounds, but I want us to just build a little bit of intuition. I don't think we're going to do a problem today yet. If we're in an elevator, and I think everybody's ridden on an elevator before, if I'm stopped on an elevator and I step on a scale, it reads my weight in pounds accurately. Would you agree with that? Okay, if I stand on the scale and the elevator starts to move upward, like it's accelerating, so it starts to go, will my weight change? Why? So go further into that. It will go up, I agree. But when you say force, I want to be more specific. What, according to Newton and Newton's laws, is really causing this to happen? If the scale starts moving up, it has to push up on me more, right? And the fact that Newton's third law says for every force there's an equal and opposite force, if the scale pushes up on me harder, in turn I must push down on the scale harder, right? Which means all of a sudden I do see that those springs compress a little bit further and the weight goes up. Going down instead, what happens with regard to Newton's laws? Why? The scale is moving away from me and it's pushing less force up on me, which means I'm pushing less force down on it, right? Now, here's a weird idea. If we stop accelerating and my elevator's just going up nice and smooth, it'll return back to normal, right? There is not a single mathematical or physical test that we can do to determine if we're moving. We can tell if we're accelerating, but just moving, you cannot tell. There's not a single test that we can do without looking at the stars and the rest of the universe that says we are revolving around the Earth right now. We don't feel velocity. We don't feel it whatsoever. It's astronomers who have worked out all the other big important parts of it. Okay, we have a fun problem to do, but we'll save it for tomorrow morning. You guys get the next 20 minutes today, and today only, to start working on anything and everything that you need to have done by the end of the quarter. Cool.